Okay, I wanted to grab a sample of this particular signal and talk about what it is, how it's developed, and how it differs from some other signals that we've also taken videos of. So what exactly is this that we're viewing? Well, this is a form of a frequency domain radar. In this case, it's an HF Doppler radar, or continuous or carrier wave type radar signature. Now there's a lot of selective fading in the signal, but we'll start to identify certain parts of the signal and analyze them going forward. But first, a little on how this signals actually differ from some other radar signatures that we've taken in the past. Specifically, over-the-horizon radars operating in a different modulation format, specifically FMCW, or frequency modulated carrier waves, or FMOP, or frequency modulated on pulse type radar signatures. This particular Doppler signature, however, really is developed to measure speed either towards or away from its particular point of reference. And that's an interesting attribute here to think about based on the frequency that we're on, which is approximately 17.450 megacycles. Well, let's talk about a little bit about what we're seeing. This signature, as it's being developed, starts out as a single carrier, and the single carrier is then put through what's called a radar pulse train. And this radar pulse train is in the form of a square wave. So it takes the fundamental carrier, and then it produces all of the odd harmonics in addition to the fundamental carrier. Now, when this occurs, we are developing a couple different parts of the radar signature. You see the main lobe here in the center view is what would be described as the coarse structure. And then if we zoom into the radar signature and start looking at the individual carriers and how they're being developed, that would be considered the fine structure of the radar signature. Now this particular signature, or type of radar, because it is Doppler, has always had a significant challenge. And that challenge was to address the efficiency of the signal and putting enough energy into the main lobe and balancing everything out. And this is fundamentally because when the square wave is produced, it really puts a tremendous amount of energy into the sidebands of the main signal. And you can see the sidebands actually develop here, the upper and lower sideband of the main lobe that we're looking at. And this is really problematic because this is a Doppler radar, and the sidebands not only take away the energy from the fundamental lobe, but they can also cause aliasing and actually curve into the main lobe and start to cause deviations or problems with how the radar is supposed to be seeing its target. So to combat this, what radar engineers have determined is the best course of action is to apply a technique called pulse profiling. And pulse profiling is applied to the signal even before it gets transmitted. And it usually is a process in which the edges of the signal, or these individual carriers, are gently rolled off, thereby reducing the amount of energy in the sidebands and putting more energy into the main fundamental lobe. But when this technique is implemented, it has one significant drawback. There's a big trade-off between range resolution and efficiency. So, in further studies, what radar engineers determined was the best course forward to combat the problem between efficiency and range resolution is to adopt two specific types of pulse profiling, and that is the cosine and the trapezoid pulse profile. And what we're seeing here on this particular signature, I would describe as the cosine profile. So it's a really interesting way to achieve both a compromise between efficiency and range resolution and really getting the best compromise for the target that you're looking at. So what I'd like to do now is actually go into the fine structure of the radar, and we'll start to look at whether or not these individual carriers are actually a form of a sine wave modulation, a square wave, triangle wave, or any other type of profile that these individual carriers can actually be made up of. So we'll be looking at it on an oscilloscope, and we'll be isolating one independent carrier now. As referenced so far, we've left the receiver into an upper sideband position, listening about 2300 cycles. So any audio that you may have heard so far is actually a product of the beat frequency oscillation of the receiver, as it is taking those individual frequencies and then remodulating them and giving us that audio component. And that's important to note because there really is no audio on these particular signatures. That is a product of the receiver only. And as the signal builds back up, you can start to see the cosine lobe here in the coarse structure, and then the independent sidebands with less energy. So let's go ahead and zoom in, and we'll turn on the oscilloscope, and we'll see what these individual carriers are going to look like, as we are going to be looking at an audio component as reference to the center of the receiver through the beat frequency oscillation. Okay, let's start to zoom in, and let's start to isolate one independent carrier now. Okay, we'll go pretty narrow there. Alright, this one is approximately 630 cycles above the center of the receiver. I'm going to put some gain into the receiver now so that we can look at it on the scope. Okay, now you can start to see that this is a sine wave, this particular format. Let's zoom in a little bit more and isolate an additional carrier. Okay, this particular carrier is approximately 137 cycles above the center of the receiver. And in this case, again, you can tell quite easily that these are sinusoidal audio waveforms that we're demodulating through with the help of the beat frequency oscillator. So this is a really great example of being able to actually start to analyze some of the individual components here of what these modulation techniques really are. Okay, you could see some different form of radars go across the screen, though. Those are ionosounds or atmospheric sounders, and we'll talk about those in additional videos. So that was a really great signature. You could see how we were able to isolate one individual carrier and look at it on the oscilloscope through the help of the beat frequency oscillator. And overall, just a wonderful example of a really interesting HF Doppler radar. Well, I hope you enjoyed the sample. We could see the coarse structure, we could see the fine structure develop, and we could see the balance between trying to null out the energy in the upper and lower sideband of the main lobe and still balancing out some of the range resolution requirements of this particular style of radar. Hope you enjoyed the sample, and thanks for watching.